Hi, my name is Sang-Hyun Cho, and this video will cover a brief overview of my work on task assignment problem. Through a series of demos, I will illustrate how to partition and assign a video analysis program in a heterogeneous distributed computing system. This video includes demo for three different aspects: analysis program, profiling tools, task assignment decision. The step-by-step instructions should allow any user to implement task assignment decision program with ease. Note that in my study, I chose human detection and recognition as an analysis program. But different analysis programs can also be used with proper profiling tools. Here are the prerequisites for running human detection and recognition program. It requires OpenCV version 2.7 with some other Python packages, such as Python image library, imutils, and numpy. HOG descriptor is used for human detection, cascade classifier for face detection, and LBPH face recognizer for face recognition.
Okay, now I'll do a quick demo on how to run the human detection and recognition program. First, you will want to get into this GitHub page and clone them. Once you've done that, you'll see under the human detection tracking methods directory, you first want to create a face model that can be used for face recognition process, such as the subject shown here. For my study, I had frontal side face taken from multiple angles for 32 different subjects. Then you will want to create a trained model for face recognition part by typing Python create face model with the directory towards your models, which is under subjects. I won't run it right now because it takes quite a time, but let's assume that you've done it. Then now you can actually run the program by simply typing Python human detect recognition. You will have to specify the directory of the video. Let's do a test for now, and specify the resolution as well. Let's do about 570. So what it does is that it first puts a bounding box around the person and recognizes it detects a face, and it puts label on the face. By simply modifying the source code, you can extract the coordinates of those bounding boxes and the face labels.
Given a heterogeneous computing system, it is necessary to profile the cost of executing the analysis program in each computer. The cost of running a program can be measured by the execution time of each module and data exchange rate between them. Visualization tools such as PyCalGraph and GraphViz are available to provide user-friendly documentation of the source code. Take the figure on the right as an example. It shows the number of invocation and execution time measured in seconds of each module. Each node is colored differently based on the execution time, and similarly, different colored lines represent data transfer between the nodes. More precise numeric value for each communication cost between each module can be measured through Memory Profiler tool. It can show memory usage for either each function or each line of the source code. And here are other tools available for source code documentation.
To also show you a quick demo on creating the profiling call graph, you can just simply do, after installing PyCall graph and GraphViz tools, you can do PyCall graph this, and from here you can basically do the same thing here. Human detect Python with the video here, test, and resolution 640. And once you run the file, you'll get pycallgraph.png, which can basically show you all the modules, complicated modules involved in running this program.
So, I'll show you a quick demo on running the simulation for test assignment decision program. This is reposited in the GitHub and under test assignment folder. In this file, the vertex and graph classes are needed to create 3 different graphs: task graph, distributed computer graph, and a decision tree. Using these 2 classes, you can add weighted vertices and edges. First, let's take a look at the main function over here. In the main function, you need to uncomment the pre-steps here to create a matrix representing distributed computing system. Number of computers, probability of connectivity, and weight of the connection are all configurable. You will open and save a matrix file in the current working directory as such. And if you take a look at each file, each row and the column represent a unique computer ID, and the numbers represent the network bandwidth between each processor, measured in megabits per second. The distributed computer graph is then created based on this matrix. We also create the task graph, which involves multiple subtasks with respective resolutions, which can be shown over here. These numbers were based on the profiling data that I did earlier. And these resolutions can be adjusted in step 2. And the number of the task graph can be also configurable. Finally, the A* function will create a decision tree for each task graph and print out the assignment of each subtask in the distributed computing topology. So, let's run this program. So, for each of the 120 task graph, it will print out a task assignment decision where it shows the task ID and the computer ID. Below here, we can see that the accumulated turnaround time for each processor after assigning all 120 tasks. And at the very bottom, we can compare the result for the average turnaround time with the task assignment and average turnaround time without the task assignment. I won't be covering the A* algorithm here due to its complexity, but it is well documented in the source code. That's pretty much it. Thank you guys so much for watching. All the codes for human detection and recognition and test assignment will be found in the GitHub repository here. If you have any further questions, please shoot me an email through cho303@purdue.edu. Thank you.